All right. To do Riemann sums by hand, really, we can only do a few types, easily anyway. And those are ones that go up to cubic polynomials, right? Now, to do these, however, we do need a few sums, namely these four sums right here. We have to know what they add up to. Now, the first one is pretty easy, comparatively, right? So if we just add up C a total of n times, in fact, I should probably add here, this is n times, right? If we add up n copies of C, well, that's just what multiplication is, right? So this is just NC. Okay? That's probably no big surprise. Now, let's look at the next one. What if we add up the numbers 1, 2, 3, 4, all the way through n? Right? This turns out to have a pretty interesting sum. It winds up being n plus 1 over 2. Right? Now, I challenge you to think about why that's actually true. It's quite interesting. All right. Now, the next one we'll need is the sum of all the squares. 1 squared plus 2 squared plus 3 squared, all the way through n squared. This has a quite interesting sum, n times n plus 1 times 2n plus 1 over 6. Right? So that's quite an interesting sum. A little bit different, but it's there. And finally, when we add up cubes, now this one, in a very interesting twist here, oops. One of these days I'll stop doing that. In a very interesting twist, this one turns out to just be the square of that one. N squared, n plus 1 squared over 4. So quite interesting that this is just the square of that. Now, I think there might be formula for higher degree sums here, like I to the 4th, but I do believe they start getting quite cumbersome at that point, so we won't really bother. So we're going to stick with just these here. So let's look at that Riemann sum we did. Again, our same example here. From -2 to 2. All right. So what we want to do here is by hand compute that Riemann sum. All right, and then take the limit of it. So we have to pick, certain things here. We have to compute an xi star, and we need, I should write these in the other order. We actually want to start with delta x, and then we're going to need an xi star. All right. So let's start with delta x. Delta x is going to be b minus a over n. So this is 2 minus -2 over n, which is 4 over n. Right? Delta xi, again, we can use left endpoints, right endpoints, or midpoints for this. My recommendation is do the right endpoints. It's the simplest one here. Right? So in this case, we get -2 plus 4i over n. Okay? So now that we have xi star, we need to compute f of xi star. Right? So that would be 4 minus, I'm going to swap the order of these here. Right? So we just plugged in this expression right here into f of x. So now we multiply this out. So 4 minus, here we have 16i squared over n squared minus 16i over n plus 4. nice enough, these constants cancel in this case. They don't have to, but they do here. All right, so my area, or sorry, let's do this. Let's just write down the Riemann sum first. So f of xi star delta x. So f of xi star, let's distribute that negative sign. So this becomes 16I over n minus 16I squared over n squared. Okay. And then this will be times delta x. Oops, I forgot the sum. There we go. So now that we have that, let's distribute this out. And what we want to do is split it up into a sum for each power of I. All right, so we're going to multiply this out. So this is 64I over n squared minus 64I squared over n cubed. All right. So what we're going to do here is use some properties of sums. All right. So these properties of sums say that I can split up a sum over an addition or a subtraction, and I can factor out constants. So much like how limits and derivatives work. Right? So that means for the first part here, this one, I'm going to factor out the 64, or let's do this piece by piece. I equals 1 to n, 64I over n squared, minus, so I'm going to add these up and then subtract adding up all of these. Okay, now that I have that, I want to factor out everything that's not an I. Because this sum is adding up over i's, everything else can get factored out. Oops, see, I already forgot to do it. 64 over n squared, I equals 1 to n of I, minus 64, this time over n cubed, I equals 1 to n of I squared. And now, these two things, now remember we had formulas up here for those. We're going to pop those in now. Okay. This is 64 over n squared, n plus 1, actually we don't need that one, over 2, minus 64 over n cubed. Maybe we should move this to the next line. Right. So the I squared is n plus 1, 2n plus 1 over 6. Okay. And now we want to take the limit of this thing. Right. So the actual area is going to be the limit as n goes to infinity of that Riemann sum. Right, I just want to remind you of this part. And we found out that this limit is, let's simplify what we can here. So we get 32 n plus 1 over n squared. All right. And then minus, let's see, 64 doesn't divide by 6. But here, so we have 32 n plus 1, 2n plus 1 all this over 3. N cubed. 3n cubed. Right. So now using what we know about limits here, we know that, the top here, this is degree 2. The bottom is degree 2. So the limit as we go to infinity is just going to be the ratio of the coefficients. This is going to be 32 over 1. Right? And here, this next one we want to look at, all right, well, what is this? So this is 32 times, so the top is degree 3, bottom is degree 3, right? So the top has coefficient 64. The bottom has coefficient 3. All right. So let's go ahead and give these a common denominator. So that's 96 minus 64 over 3, which is 32 over 3. Exactly as we had before. Right? So if getting these two numbers here is a little mysterious at the moment, multiply out these expressions right here. Right? Multiply them out, and then I think you'll have an easier time seeing it. Right? So I just wanted to show you real quick kind of what the idea would be for doing these by hand.